Hello, everyone. Uh, Thanks for joining today's event. We're really excited to have Kate and Grace giving this talk about event-driven reactive systems. Um, some housekeeping. At the end of this, we're going to have our usual JetRains raffle for 1 year of one product license. So stay tuned till the end. We're probably going to make a question. So if the presenters can help us preparing, think about a question that we can make at the end. Not too difficult, so we can get a quick winner. That will be great. Another thing, if you're not familiar with our website, I'm going to show it right now there. Here you can find the upcoming events. Apart from meetup.com, we publish here the events. We're soon going to have the recordings and links to our YouTube channel where you can find previous events. You can find the link to our Twitter handle where you can get real-time updates about new events and all things that we're doing. So if you have not bookmarked this website, or if you're on Twitter, please follow us. And I think that's all from my side. So without further ado, I'll pass it over to Grace and Kate. Thank you.
Yeah, so just a few things before we start. So if you guys have any questions, you can send the questions in the YouTube chat. We are going to have some time to answer questions at the end of the session. So yeah, we're just really happy to have today Kate and Grace. They both work for IBM. Grace is a developer advocate, and she has been working with Open Liberty and the Reactive platform. And Kate Stanley is a software engineer, and she has experience with event streams, and they live in the UK. So we really thank you for doing this. I know it's really late for you, and with no further to do, I will let it to you, girls.
Thanks so much for having us. It's lovely to be able to sort of interact with you guys. And yeah, as you said, any questions we will be answering at the end. So feel free to stick those in the chat and we'll get around to those. But thank you for joining us for our presentation all around sort of reactive systems and event-driven architecture. So reacting to an event-driven world. So this has already been introduced. My name is Grace Jansen. I work with Kate in the UK. If you couldn't tell from our accents or the dark from sort of it being so late, but yeah, I work primarily with Open Liberty and reactive systems, sort of any reactive technology within the Java and the JVM ecosystem. And I'm presenting with Kate.
Hello. Yeah, thanks again for having us. So I work at IBM as well. I work on a product called IBM Event Streams, which is a fully supported Kafka offering. So I do a lot of speaking about Kafka. And yeah, let's get started. So the first thing we're going to do in this presentation is get some coffee, which is kind of fitting because it is quite late here in the UK, although ironic because neither Grace nor I actually drink coffee. But we know that lots of people like to drink coffee, and there are plenty of coffee examples out there. So let's look at one such coffee example. So we're going to use this coffee shop demo as an example to talk about why you might start introducing event-driven architecture into your applications. So in this example, we have some coffee lovers, and they're going to order some coffee from a coffee shop. And then we have a barista who's going to make and serve up the orders. So in this first example, and you can go see the code at the link at the top, we're going to use HTTP to communicate between the different parts of our application. So the coffee lovers send the HTTP request into the coffee shop. It then receives that request, forwards it on to the barista to place the order. The barista will make the coffee and then return back down the chain to the coffee lovers. Now, this works okay if we just have one or two coffee lovers. But in reality, we will probably have a lot of coffee lovers. So what happens if we have lots of coffee lovers? Does this kind of scale? Well, what you'll find is actually the coffee lovers aren't getting a very reactive and responsive experience from this coffee shop demo. They come in, they make their request, and then they actually have to actively wait for a response while the barista makes the coffee for it to come all the way down the chain. And we've got some blocking going on at the coffee shop, because if coffee lover number 1 has placed their order, they're actually blocking the coffee shop from taking any more requests until the barista has made the coffee and returned it all the way down. Now, there are some things you can do with HTTP requests to make it a little bit more asynchronous and not have blocking threads. But actually, in reality, if you do run this demo, you will see that when you're running HTTP everywhere, it's not the best architecture. So how can we improve this? Well, we can introduce something called event-driven architecture. So event-driven architecture is a way of building systems so that they communicate by passing events or messages. So here we have our event-driven messaging backbone. And you can see we have a set of different applications, so they're microservices. And we have some that are publishing, some that are consuming. And actually, some of them are both publishing and consuming. So you can see here that S2 is consuming events from S1 and then passing new events into the event-driven messaging backbone to pass on to S3, etc. So we have this idea of event-driven architecture, and it can be added into our demo. So here we have our event backbone. And if you run the 2 different versions of this application, you can see there's 2 versions if you go and look at the code, then you'll find that actually the event backbone option does really help. So in this situation, we still have a HTTP request for the coffee lovers, because when you place your order, you really want that response that says, yes, I've received your order. But we now have an event backbone for the communication between the coffee shop and the barista. So the coffee shop will create an order and put it on the event backbone, and then the barista is free to pick up those orders and process them as and when it's ready. Then, once the orders are complete, they can put them on the queue that will go up on the board for the coffee lovers to collect them. So running these 2 options, we actually do get better, more reactive and responsive experience running with the event backbone. And often when we're looking for an event backbone, the de facto choice is Kafka. So I don't know if who on the call is aware of Kafka or if you aren't, but these are the key features that we're looking at, particularly around the sort of event backbone for event-driven architecture. So Kafka is an open source distributed streaming platform, and these are its key characteristics. We have stream history. So in Kafka, once you put a message into Kafka, anybody that's consuming those messages, they're not removed from Kafka. There are other messaging systems that act that way, but Kafka doesn't. It provides stream history. You can reread the same message if you want to. This enables very scalable consumption within Kafka, and it's really designed to handle a large number of producers and consumers and a large amount of throughput. It is designed to have immutable data being put into Kafka, so your messages being passed around should be immutable, and it's distributed and designed to be scalable and highly available. So we have all these great features of Kafka, and it's often led to us being able to ask this question. Is your coffee shop non-blocking and highly responsive? Or rather, is your microservice system non-blocking and highly responsive? Well, we have this great technology, Kafka, and we have these examples that show if you move to an event-driven system, it's a lot better. So it's really tempting to answer this question with, yes, of course it is, I'm using Kafka. But actually, that's not quite the whole story, is it, Grace?
No. So although Kafka, as Kate has pointed out, is a fantastic tool, and adding an event-driven system can enable greater asynchronicity within systems like this, we still need to think about the entire application as a whole. We need to consider, is there any blocking or any bottlenecks anywhere else in the system that could potentially stop it from being highly responsive? That's why we need to consider reactive systems. So we need to consider the various levels of the system that we're building and try and take out the blockages from that system. And to do that, we're going to look at our Barista example again and go through some of the problems that we might face and why the reactive behaviors that we want to implement are important to consider, as well as using tools like Kafka. So the first thing we need to look at when we're looking at reactive systems is the Reactive Manifesto. Now, the Reactive Manifesto was a specification designed and written back in 2013 by a group of individuals who sort of wanted to document out the different behaviors that we want to see from reactive systems and applications. So there's 4 key behaviors. Now, the first of those is the underlying behavior, which is message-driven. So this is all about having a really asynchronous message-driven backbone. Now, interestingly, in the initial Reactive Manifesto, they actually had event-driven at the bottom of this diagram, but they recently, well, in 2014, they switched in Reactive Manifesto 2.0 to message-driven. And if you want to find out more about why they did that switch, there's a whole blog post that you can check out. But why message-driven and why not events, and what's the difference between the two? Well, let's take a look at what a definition is for each of those. So we've got a definition on the left-hand side here of what a message is. So a message here is an item of data sent to a specific location, whereas an event is a signal emitted by a component upon reaching a given state. Now, interestingly, you can actually have a message that contains an encoded event in its payload. So you can kind of have a measure both, I guess. But importantly, what matters here is actually for Kafka, if we're using Kafka as our message-driven tool, it actually doesn't matter. If you take a look at Kafka's website, for example, and take a look at what it offers, it never mentions events or messages. Instead, it mentions records. So you can see here, it's all about publishing and subscribing to streams of records, storing records in a durable way, and processing those streams of records. So actually, you can use Apache Kafka for both event-driven systems and message-driven systems. So it can be a great tool to use for that asynchronous message-driven backbone we need as the backbone for reactive systems. Now let's take a look at some of the issues we might bump into by just shoving in Kafka into this Barista example, but not actually considering the other reactive behaviors and potential points of blocking within our system. So the first issue we might face is, well, there's a lot of coffee lovers in the world. So what happens if all of us go and get a coffee from the same coffee shop at the same time? That's going to be a huge influx of coffee lovers to our system. So the system is now going to have a much greater load on it, and therefore it's going to need to deal with a greater number of records or messages. And that means, in our example, a greater number of coffee orders. So that's fine. It all goes onto the event backbone. And so as coffee lovers, we can still go and sit down and chat and wait for our orders and, chat about Java, as we all love to do. So we can continue doing that because we have this asynchronous feedback from the board. However, we still have a point of blocking in our system because we have one barista. Now that one poor barista now has to make all of those coffee orders, and they're not superhuman. It's going to take time. So by having this blocking resource within here and no ability to scale that resource, we're causing blockage and we're causing this more synchronous, non-responsive behavior because our barista is going to take more time to get through those coffee orders. So this is where the characteristic of elasticity is really important. Now, elasticity in this regard describes being able to scale resources both up and down depending on the load to your system. So being able to gracefully deal with increased load by scaling up resources, but also being able to scale them down so we're as cost effective as possible. So imagine in our example, if we built in elastic behaviors to our system. Well, in this case, we could scale up our resources. So scale up the number of baristas so that we could deal with the influx of coffee orders coming in. This way, multiple baristas can be working on the different coffee orders so that we can make a much quicker, more responsive system for our coffee lovers. Let's take a look at a different problem we might run into in our system. So let's imagine in this barista example, we have a further component. So you could, in this case, we're calling it a serving table, but this serving table basically represents sort of a downstream component or even a third-party component, like a third-party database, for example, or anything that sort of processes that data coming through. So in this case, our serving table is the point at which once our barista's made the coffee, he has to place them on the serving table for our coffee lovers to come up and collect. Now, what happens if our coffee lovers are being particularly lazy today and taking a long time to come up and get their coffee? Well, that serving table is going to get fuller and fuller and fuller to the point where it's completely full and our barista's having to juggle coffee to try and keep it up. Well, at this point, our barista's hands are full, the serving table is full, and so at this point, the barista can't continue processing the records coming through because he can't make any more coffees. And this is essentially signifying that downstream component either getting stuck in a process of some kind, going down perhaps, and basically meaning that we can't continue processing those records coming through. So in this case, it's a potential point of failure that could cause our system to become unresponsive because we're not able to put any more coffee orders through. So in this regard, we need to start building into our systems resiliency. So building into our systems resiliency means that we're building this ability to gracefully handle these potential failures. Now, as amazing as we are as software developers, none of us can predict every possible potential failure that our systems could come up against. And so it's really important that we build in this inbuilt resiliency so that we can deal with failures that we may not have expected, or maybe we did expect, but we want to be able to handle gracefully. So building in this resiliency into the Barista example, for example, it might have been useful to build in some sort of feedback mechanism to come from the barista back to the system to let them know, slow down on the coffee orders, or it's going to be a while because it's a bit stuck further down. Can you slow down the number of records or the number of coffee orders coming in? So that form of feedback is an important mechanism that we often use in reactive systems to stop components becoming overwhelmed and to stop those, or at least try and prevent those potential points of failure. So these are three of the reactive sort of behaviors, but by utilizing each of them and building them into our systems, what we're actually achieving is this last behavior, which is to be responsive. And that's the whole point of reactive systems. We want to be able to respond to events and to state changes and to any change within our system as effectively and efficiently as possible. So we want to be able to be as responsive as possible so that we can truly be a reactive application for our end users. So by implementing these different characteristics, these 4 characteristics, we can really create a reactive system for our users at the end of it. So these are the 4 characteristics we need to really consider when we're building applications, as well as using tools like Kafka. But everything I've said so far has been fairly high level. How do we actually go about implementing these characteristics into our applications and building reactive systems? So to do that, as I mentioned before, we have to think about the different layers of our application. Now, as Kate mentioned, Kafka is a fantastic tool, and it's great for helping us deal with the data level. But that's not all our application is. It's not just a huge bundle of data. We have microservices in there communicating with other components as well. So we need to consider that. So we've got an example here of 3 microservices. It's a fairly basic application, and yours are probably a lot more complex than this, but it's just to show you an example of what we need to be considering. So the first stage is we need to be considering how our different components interact with each other, how they communicate with each other. That might be how our different microservices within our application communicate, but it might also be how our microservices communicate with other third-party applications or downstream components. And that's where we utilize things like reactive architecture patterns. So we've got a few examples here of what reactive architecture patterns can include. This isn't an exhaustive list. If it was, we'd be here all night or all day for you guys. But these are 4 of the most commonly used ones that we've come across that we'll also be going into a bit more detail in for some of them later. So the first one we've got here on the board is CQRS. So CQRS is, it stands for Command Query Responsibility Segregation. What that basically means, broken down, is you're separating out the read and the write APIs. And what that enables is higher availability of the data so that we can respond more effectively and more efficiently to it. Then we've got things like circuit breaking. So circuit breaking, if you've done electronics, you've probably come across a circuit breaker before, but a circuit breaker is essentially a mechanism in which we can help overloaded or stressed or sort of malfunctioning components to give them the time they need to get better and get back to a state where they can perform as they should be. So what it does is usually you'll have some kind of parental actor or parental microservice who's able to detect sort of continuous repeated failures from the same microservice or the same component. When they recognize that, they then stop any requests going to that component. So they implement a circuit breaker, and instead they send those requests to replica microservices or components. What that means is it gives the component that's under extreme stress or load a chance to get through that processing or get through those requests, or maybe come back up again if it's gone down. And then once they come back up again and they're able to perform as they were, they then get those requests rerouted back to them. So the circuit breaker is stopped. Then we've got sagas. So saga is essentially sort of a mechanism to take traditional transactions that we would have normally done in a monolithic architecture and do it in a more distributed manner. So we create these sort of multiple microtransactions, and they have a fallback behavior to account for things if they potentially go wrong partway through. So it's more a sequence of local transactions where each transaction updates data within a single service. And then the last one we have here is back pressure. So back pressure is essentially another form of feedback, and it's essentially what I described with the Barista example. So back pressure is feedback from a downstream component to an upstream component. So it enables the downstream component to tell the upstream component if it's under stress or extreme load, and it helps to rate limit the messages or the records or the events coming to it so that it doesn't become overwhelmed or stressed. So this back pressure is actually a pattern that's offered as a default in many of the reactive frameworks that you can utilize. So as I said, these are just some of the reactive patterns that you can use, not an exhaustive list, but some of the really useful ones that often get used in reactive systems and reactive applications. There are loads of blogs online that list more if you did want to go and explore more options. So we've looked at the system level. Now let's dive down to a deeper level. So we also need to consider what's in our microservices. So we need to be building microservices individually that are also reactive and asynchronous and non-blocking. And to do this, we can implement things like reactive programming. So what is reactive programming? So we've got a basic definition here of what reactive programming really is. And it's essentially a form of asynchronous programming where we drive forward the logic with the availability of new information instead of by a thread of execution. So it's all about implementing this logic within your microservices that's more asynchronous and more non-blocking. And to do this, there are several patterns that you can implement. So the first of those is if you're familiar with Java and you're a Java developer, which many of you may be, then there's futures. So futures are essentially a promise to hold the result of some operation until that operation completes. So futures are often used. We've got things like reactive programming libraries. So reactive programming libraries are for composing asynchronous and event-based programs, and they include libraries like RxJava and Small I Mutiny. And then we've got things like the reactive stream specification. Now, the reactive stream specification was created in order to help better handle asynchronous data streams in a non-blocking manner, while also providing that all-important back pressure to stream publishers. And reactive streams is actually utilized in many of the reactive frameworks and toolkits we'll discuss later on. So these are some of the sort of implementation techniques that you can put into practice when designing your applications to help them become more reactive, more asynchronous, and more non-blocking. But how do we utilize these when we're building a system that uses Kafka?
Well, we've already said that Kafka is a really great tool. It has some great features that lend it to event-driven, but you can't just add Kafka and then assume you're going to be reactive straight off the bat. So what do we need to actually do when we run Kafka? How do we configure it to make it properly reactive? One of my favorite things about Kafka is the fact that it is so configurable. So you can set it up exactly for your specific use case. What that does mean is it is worth being aware of some of the more fundamental configuration options within Kafka so that you can make sure you're configuring it to not, leave yourself a hole. So how do we do this for resiliency within Kafka? Well, the great news is that Kafka does have resiliency built in. So it's built as a distributed system. The Kafka servers are called brokers. So if you have a single Kafka cluster, it's normally made up of one or more brokers. The sort of standard starting point is 3, and you'll see why in a minute. So we have these 3 brokers, and this is where all of our data is separated across. And now in Kafka, we already talked about that we deal with records. So rather than calling them messages or events, we just call them records. And these records are stored on the brokers, and they're stored in topics. So all of the records that you have are broken down and grouped by topic. And it's up to you to choose how many topics you want to have. So you can group it by, for example, you could have one topic that just deals with customer addresses or updating specific orders. It really depends on your use case, but you define a topic and which records are going to go to that topic. Now, within a specific topic in Kafka, that's also broken down again into partitions. So a topic within it can have one or more partitions. And we'll see why partitions are important a little bit later on. But for Kafka itself and the resiliency that it has built in, the important thing is we have these 3 brokers, and these brokers are running on different machines and they should be distributed. So if you had multiple availability zones, then you would put one in each different availability zone. Then, for a specific topic and a specific partition, within Kafka you have one broker which is elected as the leader. All of the other brokers are then followers. So if you have 3, then you can get a quorum and agree on who the leader is. And the really great thing about Kafka is that for a specific topic and a specific partition, it will automatically make sure that any followers will get copies of the records that get sent to it. So producers and consumers, so applications that are sending records into Kafka and reading them back down again, they all communicate just with the leader. And when you create your topic, you decide how many followers you want to have. So in this situation here, I've asked for 3 replicas, so I get 1 leader and 2 followers. And Kafka will make sure that all of my records get copied onto the following brokers. That then means that if something were to happen and my broker were to go down, I already have a copy of the data on the follower broker. So what Kafka will do at this point is automatically run what's called a leader election, and it will elect a new leader, so in this case it's now broker 2, and it can start working straight away because all of the records are already there. All of the clients will get told, you need to come and talk here now, this is your new leader, this is where you need to get your records from in future, and they'll automatically switch across. So this is the way that Kafka provides resiliency and allows you to have availability and uptime within your Kafka cluster. So we've talked about resiliency in Kafka itself and how you can handle a broker going down. But how do you make sure that you have resiliency in terms of your producers and consumers? So we'll talk about producers first. When you're producing records into Kafka, the sort of guarantees that you'll normally consider is at most once or at least once. You can get exactly once within Kafka, but it's aimed specifically at applications that are written using the Kafka Streams library, so it's quite a specific use case. But when you're looking at delivery guarantees, generally you'll consider, do I want to make sure that I get this message or this record at least once, so I could get duplicates, or at most once, so I don't mind if I drop a few. If you're looking for a flow that is fully resilient and guaranteed, then obviously you need to go for at least once. The way you configure this within your producer is to set ACKs and retries. So we've already talked about making sure that you have replicas set up, and when you create your topics, you need to consider your replication factor. But you also, when you're producing, need to set the ACKs. So ACKs is short for acknowledgements, and you can set it to one of 3 values. So you can either say, set it to 0, I don't really care if this record gets there. I want to, make sure there's not an initial error, but if my leader goes down and it gets lost, it's not a big deal. That is the best way to get high throughput in Kafka, but it does mean that if your leader broker were to go down before replication happens, you've lost your record. 1 is similar in that it doesn't wait for any of the replicas. But if you set ACKs to 1, it will make sure that the leader at least is happy that it's fully received the record. The setting that you'll need to choose if you want full resiliency and to make sure that even if a broker goes down, you'll still keep your records, is to set ACKs to all. That means wait for all of the replication to happen to all of the followers before you tell me that my message has been received on my record. So you need to consider what ACKs you're going to set and how much you care if a broker goes down and what is that going to do to your resiliency. Alongside that, you will need to consider retries. So most of the Kafka clients do have retries already configured and they have a default number, but you might want to look at increasing the number, decreasing, depending on what resiliency you want, but also consider ordering. So if you have retries set, then you need to look at whether you're going to be retrying and trying to send multiple records at once, and will you get out of order. So the 2 key configuration options to consider from a producer side are ACKs and retries. So let's look at the consuming side. consuming in Kafka and resiliency is all around something called offsets. So because Kafka has an ordered set of records and you can't change them, they're idempotent. So the records, once they go in, that's where they remain. They're all given a number, and numbers start from 0, go upwards. When I'm producing new records to Kafka, I always add to the end, so offset 6, 7, etc. Now, as a consumer in Kafka, the offset that you're currently at is actually stored in a Kafka topic. It's called the consumer offsets topic, and this allows applications to go down, and then if they then come back up again, they can continue reading off the topic. You need this in Kafka because, unlike other messaging systems, the record can be reread. So that's really great because you can reread history if you need to, and you can have lots of different consumers running, but it does mean you need to keep track of where you are. And there's 2 ways for you to tell Kafka where you've got up to in the stream of records, and that's using manual or automatic committing of offsets. So let's look at the differences and kind of pros and cons of the 2. So the easiest, and the one that people normally start with, is auto commit. With auto commit on, you don't have to write any code to talk to Kafka to tell it about where you've got to in reading records. The client will do it for you. So in this example, we have a topic, which is in Kafka. So our coffee orders here are our records. And then the barista is an example consumer. If I've got auto commit on, my barista might read the first order, so they've consumed the first record. And then asynchronously, under the covers, my client will tell Kafka that I have read that record. So I'll get a little tick to say, yep, this is where I've got up to. If my consumer were to go down, so in this example, say my barista drops his cup of coffee that he's making. When he goes to check to see where he's got up to, and when he comes back up, he'll see that he's already consumed the coffee order. So he'll pick up the cappuccino order next. Then he'll continue to the latte and serve both those up. So in this case, we've actually lost a record. It's still in Kafka. We could still consume it if we wanted to, but from a consuming side, there is one order that is missing. So let's look at the manual commit. So in manual commit, this implies that you've actually written a line of code in your application that is telling Kafka I'm committing this offset, this particular number. So in this example, if I read the coffee as a barista, consume my coffee order down, process it, I won't actually add that line of code to do the commit until after I've finished processing. So in this case, for the coffee order, me finishing processing a record is me serving up the coffee. So once I've served up the coffee, I then tell Kafka, yes, I've read this record. If you do it this way, what it means for your application is that if your application goes down when it's halfway through processing a record, when it comes back up, it can just reread the same record back down again and reprocess it. So in this coffee example, if we do it this way, it means we get every single order. So when you're looking at resiliency in your consumers in Kafka, you do need to think about, are you going to use auto commit or manual commit? And if you're going to use manual commit, at what point have you finished processing the record, and are you happy that if the application goes down and comes back up again, that it will move on to the next record in the topic? So we talked about resiliency and the resiliency that's built into Kafka and how you can configure your producers and consumers. But what about elasticity? How do you scale Kafka? Well, this is where partitions really come in. So scaling in Kafka is done with partitions. So for a specific topic, I said you could have multiple partitions. And the idea behind the partitions is, from a producing side, it allows you to spread out the load across the different Kafka brokers. So if you have one topic that's really busy, rather than one broker being completely overwhelmed by people producing to that topic, you can spread the load out. And Kafka will try to make sure that your partitions are spread across the brokers initially. Over time, you might find they sort of migrate, and there are various tools available for you to put them back. But when Kafka initially adds partitions, it will try and spread them across the brokers. Kafka is designed for high throughput and a lot of volume of records coming through and a high number of producers and consumers. the interesting piece when you're looking at scalability in Kafka is how do you scale out and have multiple consumers but have them not read the same records as each other? Because unlike other messaging systems, you have this stream history. So theoretically, you can have two consumers reading the same record. Well, in Kafka, that is achieved using consumer groups. So a consumer group is a mechanism that Kafka uses to allow different applications to work together to consume. So let's look at an example, because that's just the easiest way to explain how it works. So let's say we have two consumer groups, A and B. The consumers have started up at their individual applications, and the way they joined a consumer group was when they connected to Kafka initially, they gave a consumer group ID. And any consumers that start up with the same ID will get put into the same group. What Kafka will do is it will guarantee that between the consumers in that group, they will see all of the records. So in this scenario, it means for consumer group A, they will read one partition each. So the first one is reading partition 0, the second one partition 1, and the third one partition 2. For consumer group B, we only have two consumers. So in this case, one of them will read one partition, and the other will have to read 2. Now, the thing that it's worth bearing in mind with partitions and being aware of is the ordering in Kafka is per partition. So Kafka's ordering guarantees says within a partition, we'll guarantee that the ordering will remain the same once you've produced onto the topic for then reading it off. So connecting two consumers to the same partition doesn't make sense, because at that point you've lost your ordering. So actually in Kafka, if I stand up another consumer as part of consumer group A, it won't get any records because of that ordering. So when you're scaling your consumers, you can make use of the partitions and you can make use of the consumer groups, but you can only scale up the consumers to match the number of partitions. So when you're initially configuring your topic and deciding on your replication factor and your partitions, you need to think about how far will I need to scale my consumers up and down, and pick the partition number so that it works for that. Now you can add more partitions. So if you start with a smaller number and decide you need more, that's fine. But the slight hitch with that is if you use the default partitioner, so if you allow Kafka to decide for you how the records from the producers go into the partitions, then you will lose that ordering guarantee. The way that the partitions work in Kafka, if you send records in with a particular key, they should all end up on the same partition. But as soon as you add partitions, you lose that. So it's worth having a think, working out how many partitions you think you're going to need, and having a look at whether you care about ordering and care about things being on a specific partition. So we've now talked about Kafka and how it's resilient and scalable, some of the specific pieces that you should be aware of when you're starting to create applications with Kafka. But what about the actual Kafka applications themselves?
So let's take a look at how we can write these reactive Kafka applications. So as standard, normally in the standard Java Kafka client, you'll get the standard Java Kafka producer and the standard Java Kafka consumer. Now, these do offer some characteristics, like Kate's mentioned, that we can utilize to really make our Kafka applications, our standard Kafka applications, more reactive and asynchronous, like those configuration options and like those design sort of considerations that you need to make when you're first designing and implementing your application. But there are frameworks out there that sort of connect to and implement with Kafka that you can utilize to really create reactive applications. So we're going to look at 3 today. So 3 of those sort of reactive frameworks that do have specific connectors into Kafka are Alpakka, or Akka, the Akka framework, which has the Alpakka Kafka connector. We've got Microprofile, which has a Microprofile Reactive Messaging, which has connectors to Kafka. And we've got Vert.x, which is another framework, and that it has a specific Kafka client inbuilt as well. So these are just 3. There are other options, but these are 3 that we're going to highlight that you can utilize today. So the first one we're going to go into is Akka. So the Alpakka Kafka Connector API is the API that you'll need to connect in between Kafka and Akka. So what it does is it connects in between Kafka and Akka streams, which is the streams, the Akka version of the stream specification that I mentioned earlier. So Akka, and therefore Alpakka, which is a library within Akka. So Akka is the framework, Alpakka is the library. So Akka is a framework that's built on top of the actor model. So if you're already using and utilizing the actor model for your application, this might be a really good framework to consider to implement into your application in your system. But if you've not come across actors before, they're a slightly different conceptual model to microservices. It's not necessarily a one-to-one mapping between the two, but the actors are the primitive unit of computation within the actor-based model. And there are tons of blogs online you can read about what the actor-based model is and why Akka uses it. But Akka then links into several other reactive frameworks that you can utilize, like Play and Lagom. So if you did want to check those out, they're all open source, and you can go to akka.io to find out more. So the next framework we're going to look at is MicroProfile. So for anyone who's not come across the MicroProfile specification before, it is an open source community-driven specification specifically for enterprise Java microservices. So it's to help you really build and to utilize any APIs and specific services you might need in order to build microservice-based applications using enterprise Java. And it's built by a bunch of companies, individuals, and vendors. So IBM contributes, Red Hat, Payara, and loads of other vendors across the industry. So MicroProfile is built up of different sort of APIs and specifications. So you'll see here, these are the different APIs available. The bottom sort of half triangle that you can see here at the bottom that's in gray, they come as standard in the MicroProfile 3.3 stack. Now 4.0 is on the way out, but it's not been released yet. So we've got that sort of, those come as standard, and then we've got the standalone projects in the right-hand corner here, which aren't yet part of the stack, but hopefully will be integrated at some point in the future. And up there we have the reactive messaging specification. Now the reactive messaging specification is the specification you'd want to use for really utilizing reactive and asynchronous communication between the components of your application. And it actually builds up upon the reactive stream specification that I mentioned earlier, which isn't a MicroProfile specification, but is widely used in reactive frameworks. And it also utilizes another standalone project, which is the reactive streams operator specification as well. So the reactive messaging specification actually uses something called annotations. So it uses this incoming and is at incoming and at outgoing annotations in order to link the two channels together. Try saying at outgoing quickly, it's quite hard. So it links them together by using these things called channels. So channels are quite like literally just opaque strings. So it's just a string to connect together the inward source and the outgoing source of this data or these records or all these messages. So you can see here in the bottom diagram, we've got a method A and it's connected to method B by the channel order. And you can see that the at outgoing and at incoming order are connected by that channel. So you can also have channels that connect to external applications and external sort of messaging systems, and they're called connectors. And within MicroProfile, there is a Kafka connector that you can utilize in many of the implementations, including OpenLiberty, which is our open source application server within IBM. So the last framework we're going to take a look at is Eclipse Vert.x. So Eclipse Vert.x is another Eclipse project. So MicroProfile is also an Eclipse project. And it is a polyglot toolkit. So it's essentially based on like a plug and play model where you can essentially add the different components and libraries that you need to make your reactive application. It's based on something called the reactor pattern, which is essentially an implementation technique of event-driven architecture. It utilizes a single threaded event loop, and it includes a distributed event bus within it. So you can connect sort of this event-driven architecture all the way through your application. It's non-blocking and it runs on the JVM, but it is polyglot. So you can use it not just for Java, you can also use it for JavaScript, Groovy, Scala, Kotlin, so loads of different languages within there. And this is actually the framework that we chose to use when we were re-architecting our own application, which was originally just a Java Kafka application, to be reactive. So Kate's going to demo that now.
Yes. So this is the demo app that we wrote as part, like the precursor to writing this talk. So actually, the original reason I wrote a Kafka application was because I do a lot of talks and outreach and things in the Kafka community. And what I was finding is actually often people do the quick start guide. So there's a set of shell scripts that you can use to start running Kafka locally. And that's really great. And you can do a produce and a consume from there as well. But often it was then quite a big step to go find an actual Java application and write a Java application that could talk to Kafka. So my initial motivation was literally just to have an application I could give to people to say, this shows how to use the Kafka Java clients. And it also could introduce some of the things around offsets and what partition you're using, and start to help people understand what's actually happening under the covers when they're producing and consuming to Kafka. Then I met Grace and we started talking about the application and the problems I'd had when I originally wrote it, and realized that actually using something like Vert.x would really help me. So this is the architecture for the application. Because it's designed as a sample app for producing and consuming, it does produce to Kafka and then consume straight back again, which is potentially slightly odd thing to do, but for this demo, it was what I needed. And we also have a UI as well. So I wanted the UI to give people a flavor of what's actually going on under the covers. Now, all of the code for this application is open source, including the UI. So feel free to go over to GitHub and have a look, download the code, have a play around and see what we did. But I've got a little video here showing the application running, just to kind of give you an idea. So the application, this is the UI. I've already stood it up, Kafka and Zookeeper in the background, and then started the app. And I can start producing and consuming with a custom message. I can then see the records coming through. They are actually going to Kafka and they're coming back down to get to the page. And I wanted to be able to stop producing, stop consuming, maybe change the message, start producing again, just so people can have a play around with sending in different records. And it was actually this flow control that caused me the most issues when I was writing the application using the standard Kafka clients. And that was because when I'm writing with a standard Kafka client, I was finding there wasn't quite the mechanisms I needed to control this flow. So if we have a look at some code, I'll explain a little bit more what I mean. So in the producing side, generally everything was kind of working pretty well. Writing the producing part of the application, pausing the producing was pretty straightforward. But for consuming, if you use the standard Kafka Java client, this is the normal flow. So you have a poll loop. So Kafka consumers are expected to poll Kafka to request a new set of records. And you can poll for individual records, or you can poll for batches if you want to get better throughput. So what you do is you do the poll, you'll generally get back a set of records. You then have to cycle through all of these records, processing them. And in my case, you can see I'm doing a session get basic remote send object. So that's actually sending it along a WebSocket back to the UI. So that's my sort of processing of the records. Now, the thing with this is if I wanted to pause and consume this poll loop, I had to handle that in a different thread. So I was having to run the poll loop in one thread and then have process running somewhere else that's talking to the UI via a WebSocket, that's pausing and consuming. And I did get it working. It did work fine, but it took quite a long time for me to get something that actually made sense and it didn't overwhelm the UI with records. And it just didn't feel like it really fit with my use of Kafka. So that was when I started looking at Vert.x. So this is an example of some of the Vert.x code if you go have a look at the application. Now with Vert.x, there are some other options that are available to me. So in Vert.x, I can do this Kafka consumer create, but you can see here I don't actually have a poll loop. Instead, I've defined this handler. So what's actually happening is under the covers, Vert.x is handling the poll loop for me. So I can just give Vert.x this one function to say, call this handler when you get new records. And the nice thing is here, rather than having to have a for loop and going through each of the records, I can actually just have one function that handles each record individually, and it will just get called with the new records as they come in. Under the covers, there is a poll loop still happening, but Vert.x also allows me to handle that. So there is this resume and pause mechanism that I can use to pause and resume the poll loop. So the standard Kafka client does have resume and pause, but it still leaves the handling of the threads and what you're doing up to you. The thing I found when I was moving across to using Vert.x as part of this application was actually it gave me the toolkit to build up a reactive and more responsive experience. And actually, the way that you interact with Kafka, it just felt like it gave me a better fit. One of the really nice things about Vert.x is that if you want to handle the polyp yourself, then you can, but it does give you this opportunity to have this abstraction layer. And the Alpakka Kafka connector and microprofile reactive messaging, they go even further. So for them, the polyp is even more abstracted, and you actually just use their mechanisms for asking for new records and things like that, and they will handle the communication with Kafka for you. So we talked a little bit about some of the things that I really liked about Vert.x and some of the exciting reactive features that Grace helped me add into the application. But we've actually written a blog post where we've gone into a little bit more detail. So if you want to see exactly what steps we took and some of the other Vert.x features that we really liked when we started looking into Vert.x, then do feel free to check out the blog post here.
So in summary, hopefully we've shown you through this presentation that just sort of shoving in an event backbone, be that Kafka or any other way of implementing that, isn't a way to really achieve a responsive and reactive and non-blocking application. So you can't just stick non-reactive and Kafka together and expect to get reactive. Instead, what you need to do is carefully consider the Kafka configurations you've got set up and implement those to be the best they possibly can be in order to achieve those reactive behaviors we described earlier in your own systems and applications. But you are not alone. The open source reactive community is vibrant and thriving and has loads of different options for you to choose from when you're looking at different frameworks and toolkits and libraries to help you implement these non-blocking asynchronous behaviors within your own system. So to help you out with this, we have a few resources for you to get hands-on after this presentation and after this meetup. So the first of those is a series of hands-on labs. So if you want to get hands-on with some of these APIs, these labs are based on the microprofile specification that we mentioned earlier and that reactive messaging spec specifically. So we've got 4 labs here. We're still adding to them every month, so there'll be more coming out later this month. But you can hit those up to check out how to go from synchronous to asynchronous, how to implement reactive messaging within an application, and how to test reactive applications using tools like microshed testing. So feel free to check those out. They'll be online. They're sort of online all the time, so you can do those whenever. Another resource is a short ebook. So if you want sort of a summary of reactive systems, what they are, why you'd use them, and sort of how to implement them, check out this free ebook online that I helped author with a colleague. The link's there. It's all free and it's only about 30 pages long. So feel free to check out that free resource.
And if you're looking for running Kafka and what your options are, then do feel free to check out IBM Event Streams. So that's the product that I work on. And we have 2 different offerings. We have a fully managed offering on IBM Cloud, and then we have an on-premise version that's designed to run on OpenShift. And so that's the version that I actually work on. Kafka is something that's actually been run as part of IBM for a long time. So we've run our managed system since 2015. We're very active in the Kafka community, and Event Streams provides you a fully supported Kafka offering with some additional value add capabilities on top. So we have a user interface for managing Kafka. So that's the snippet you can see here. We also provide a schema registry so that you can add schemas to your records and allow you to evolve them over time. And we also provide options for geo-replication if you have disaster recovery, and lots of connectors as well. So if you're looking at connecting Kafka to other systems, we have things like MQ connectors that you can use. So do feel free to check this out if you want to know more about Event Streams. And oh, I should mention as well, if you want to try it for free, then the IBM Cloud offering has a free option that you can just try before you buy. So with that, we have, again, more links for you. We wanted to provide plenty of resources. So we've got some reactive resources like the Reactive Manifesto and Getting Started with Reactive. We've got some Getting Started with Kafka links. So the quick start guide that I mentioned with the shell scripts, that's really handy and is a good place to just start up Kafka and Zookeeper. If you're looking for something that is more Kubernetes OpenShift based, then look up Strimzy. That's a Kubernetes operator for Kafka. It's an open source project and Event Streams is built on top of that. And then if you're looking for reactive Kafka libraries, we've got some links to the ones we talked about today. So with that, thank you very much for listening, and I guess we'll open the floor to questions.
All right. Well, first of all, thank you very much for the talk. It was awesome. So first of all, I have a question. So are you guys gonna give us or provide us the URL for the slides, because there are a lot of links? I'm not sure if people is actually taking pictures of them.
Yeah,
So,
absolutely. Yeah, I can send those through for you.
okay, sounds good. I'll just make sure that I post those in Twitter.
I'll put it on our chat, and then if you could put it across into the YouTube chat. Yeah.
Cool. All right, Arturo, do you have any questions, Orlando?
There are a couple of questions on the live chat.
Yeah.
You want to go ahead, Arturo?
Yeah, there's actually 3 questions. One from Aki, and the question is, if the underlying server can provide functionalities like elasticity and non-blocking I/O, then what are the cases where still Kafka should be used?
So the question here, I think, was around if you're doing a HTTP request, you can make a request and have the thread not be blocking. But actually, some of the capabilities that adding things like Kafka brings in is it allows you to approach your whole kind of architecture a little bit differently. So it's not just about replacing that communication and saying, oh, well, instead of doing something that is synchronous, I'm going to do something that's asynchronous. The idea behind event-driven architecture is to actually put the events at the center of everything that you do. And when you look at one HTTP request, it is, kind of straightforward just to swap it over. But actually, if you're producing messages and events into a system like Kafka, what it allows you to do is then to continually evolve your system, make it more reactive and responsive going forwards. Because if you imagine a scenario where today you're just making coffee orders and you put the coffees on, say, Kafka, one of the really cool things about Kafka is you could then bring in another application that is just watching those coffee orders and doing some processing to say, like, oh, I've noticed that we've had 50 coffee orders today, we better order some more coffee. So although there are definitely systems, I think, where actually just making sure you've got non-blocking I/O and that you've got HTTP requests where you're not hanging threads is potentially enough. If you look at swapping and going to this more reactive responsive experience, you will probably find that actually there's more places where you can get advantages and add things that you just wouldn't have been able to do if you had stuck with just HTTP. I don't know if Grace has anything to add to that.
No, I think you covered it all.
All right. The next question would be from Tenmaya. How Kafka keeps track of the last offset read?
Yes, so that was in the committing offsets that I talked about. So in Kafka, there is a topic where all of the current offsets for consumers are kept. So the name of the topic is, I think, is __consumer_offsets. So it's often hidden. It's like there are special topics in Kafka that are often hidden. So when you run the Kafka like command line tools locally, if you search for the topics, you might not see it come up. But there's an actual topic, and in there is stored all of the offsets for the different consumers. And then as the consumers progress through the records, they basically are in charge of telling Kafka, this is where I've got to, this is where I've got to. And by default, the Kafka clients will just do it for you in an automatic basis. But often you'll find that actually you want to take control of that. So there's a setting that you can change to say auto commit offset is false. And at that point, you have to like write a line in your code to do it. So if you run Kafka, I'd encourage you, there's a setting, I don't know what it is off the top of my head, but if you're running like the shell scripts to look at the Kafka topics, there's a mechanism to show internal topics. If you do that, you can see them and you'll actually be able to consume and like have a look what's going on in there.
All right. We have 3 more questions. One from Franklin. Open API specification allows us to know the API interfaces or resources in a friendly way. How does Kafka or similar applications allow the same?
Yes, so that's where schema registries come in. So I mentioned it right at the end. We have one as part of event streams. There's a few different open source options as well. And basically what a schema registry does is similar to your open API specification, where it provides a specification for the API. The schema registry provides a schema for your record. So on a very simplistic level, if you don't have a schema registry, what you would have to do is put some JSON or something in your actual message that says this is the structure of my message. Obviously, that's not ideal. So the way you would normally do it is you store that structure in a schema registry, and then the messages that get passed into Kafka will have something in the message or as a header that will indicate which schema to use. And then the applications can pull the schema down from the schema registry and use that to decipher the record. So I would highly recommend, if you're using Kafka, to add a schema registry to it. If you use event streams, it comes built in, but there are some other open source ones as well if you're using an open source Kafka.
Okay. The next question is from Agustin Ramos. Most of your implementation of a reactive architecture is based on Kafka as the messaging layer. What other options would you consider?
So you don't necessarily have to go with Kafka, for example. You can go with other messaging implementations and sort of external messaging technologies like MQ, for example. There are different mechanisms to do that. So for example, if you're going to be using Akka, Play, Legom, you might want to use their inbuilt messaging system. But yeah, I wouldn't say it's necessarily limited to Kafka. It's basically any messaging technology you can pretty much build a reactive system on top of. Kate, would you agree?
Yes, definitely. So I think the thing to bear in mind is for this tool, we focus on Kafka partially because it is gaining so much popularity and because it is very configurable. So it can be easy to just set it up and not realize there's all these configuration settings you hadn't really considered. But I think with any messaging system, it's worth going back through the Reactive Manifesto and think about how are you integrating with it and are you doing that in a reactive and responsive way.
All right. And the last question is from Gopi. Are there monitoring tools for Kafka?
Yes. So Kafka actually does produce JMX metrics. So that's the normal way that people integrate with Kafka for monitoring purposes, because there's plenty of tools that can like scrape and process JMX metrics. So that's the normal mechanism that people use. And then they'll get, I think with event streams, you can connect things like Datadog and Splunk. But for running open source Kafka, you can do similar things.
All right. And I think those were all of the questions we had in the chat window. Orlando and Abel, do you have any more questions?
Well, I had one that probably they know about. I mean, I know that actually I'm very interested in doing the quick labs with microprofile because I hear that microprofile is like getting more and more popularity. So what do you think about microprofile and how do you see the adoption in the industry?
I think the great thing about microprofile is that you don't necessarily have to implement all of the specifications. So you can pick and choose which specifications that you need and are important to your application. But not only that, it's the fact that microprofile is built by so many different vendors that it really is a community project. So if you want to get involved and you want to sort of help to guide its development to include features or tools or implementations that you need in your application, that's possible because you can get involved in the community and you can help to drive that innovation going forwards. The nice thing about it is because it's built by multiple different vendors, it can be used with multiple different implementations. So regardless of which runtime you're running underneath it, whether that's Quarkus, OpenLiberty, or any other runtime, you can implement microprofile with that fairly easily. And it has standards across. So even if you switched runtimes with your application, you could keep the programming logic within your application the same because the syntax will be the same because you're using microprofile, which is applicable across all of them. So I would definitely recommend that. And the nice thing about the quick labs we have here is the environment is all set up for you online. So you don't need any prerequisites. You don't need anything downloaded onto your local machine. You can just do that all in our environment online.
That's awesome. Thanks.
Yeah.
Orlando, you have any questions, Orlando or Arturo?
Nope, not from my side.
I'm good.
All right.
So now it's time to the presenters to make a questions for our raffle.
Oh, I love it. Okay. Kate, do you want to ask one or shall I?
I did have an idea of one.
Go for it.
Are we doing
Great.
one we've talked about in the presentation, or can it be slightly?
Yeah, hold on a few seconds.
Okay,
So
I got too
let's put
excited.
the same page for the people in the stream. So this is gonna be the questions for the raffle or the JetBrains license. So the first correct answer to pop up in the YouTube stream chat, that's the winner. Okay, so
If it is the correct answer.
Importantly.
Yeah, and keep in mind we have a slight delay from
Mhm.
the real-time chat and the YouTube stream, but it's just a few seconds.
Cool.
all right. I think we're
Kate,
ready.
I'll let you go for it.
Shall I go then? Which company originally created Kafka?
Ooh. Good question.
Let's see if we get an answer, a correct answer.
Because I don't think I said it in the end in this presentation. Be interesting to know if people know.
Any answers?
No answer so far.
Not yet.
Everyone's busy checking their notes going, did she mention it? Did she mention it?
The first one is MH Joe. He says LinkedIn. So I think
That is correct.
Yeah.
we have a
Yeah,
winner.
it's sourced by LinkedIn.
All right. Well, so I guess if I'm not sure if it's actually very safe to leave the do you know that person, Orlando Arturo?
No.
No, but
Okay.
if you can send us your email at info@cltjug.org, send us your email and we'll send back the IntelliJ license. And please, please, please activate it. Sometimes we raffle licenses and then we get a notification from JetBrains that they're not getting activated. So if you're not going to use it, I mean, you can give it away to someone that needs a license.
Yep. All right. I think that's all right, guys. So again, Grace, Kate, thank you very much for doing this. It was an awesome session, and I hope we see you around in some other conference soon.
Would absolutely love to. Thank you so much for having us.
Thank you so much for having us.
Have a good night.
Thank you.
Thanks.
Thanks,
Bye.
everyone. Hope to see you on the next one.
Thank you.